we are investigating radiation characteristics of what is called a Hertz dipole. We saw in the last lecture that Hertz dipole is a small current element. That means, if you imagine a small piece of wire which is carrying some current, then we can find out the vector potential due to that small current element, and then from there we can find out the electric and magnetic fields. So, in the last lecture, for the Hertz dipole, which is a small current element, we derived the vector potential and the electric and magnetic fields, and we saw that for the Hertz dipole we have a magnetic field which has only one component, that is only phi component, whereas the electric field has two components. One is the r component, which is the radial component, and other one is the theta component. We also saw that these fields have three types of variations as a function of distance from the Hertz dipole, that is a field which varies as 1 over r, the field which varies as 1 over r square, and the field which varies as 1 over r cube. And then we understood the different phenomena which are behind these three types of fields. So, we said 1 over r square field is the induction field, 1 over r cube field is what is called electrostatic field, which is on the ends of the current dipole you have accumulation of charges. So, we have essentially a bundle of charges which are sitting at the ends of the Hertz dipole. As the current oscillates, this charges also oscillate. So, you are having a dipole, and because of that dipole you get electrostatic field, and that is given by this term. So, its variation is 1 over r cube, and then the important term which in which we are interested now in is the radiation field, which varies as 1 over r. So, as you go away from the dipole, that is the field which is the radiation field essentially dominates, because these two fields die down very rapidly as we move away from the dipole. So, we essentially divided the fields into these categories, and then we said, depending upon the distance from the dipole, we can call these fields as the near field or the far field, and we had a distance which is the reference distance, which is lambda by 6. So, if the distance is much less than lambda by 6, then electrostatic and induction fields dominate, and we call those fields as the near fields, whereas if we go to a distance which is much larger compared to lambda by 6, then the dominance is by the radiation field. And then we saw that radiation field has only two components, which is theta for electric field and phi for the magnetic field. We had also seen some interesting property for these fields, that is the ratio of E theta and H phi for the radiation field is equal to the intrinsic impedance of the medium. That property is same as what we had seen for the uniform plane wave. However, in this case we have a constant phase surfaces which are the spheres. So, we call these waves as the spherical waves. However, spherical waves essentially have all the properties which the uniform plane wave has, that is the electric field, the magnetic field and direction of wave propagation are perpendicular to each other, and also the ratio of the electric and magnetic field is equal to the intrinsic impedance of the medium. Today we try to see more characteristics of the Hertz dipole, and essentially two things we are interested in when we talk about the radiation. One is, for a given current in this Hertz dipole, how much power will be radiated in the space, that means how much power actually will be carried by these fields. Second thing, what is the directional dependence of this power flow. So, the feature which captures the directional dependence is what is called the radiation pattern of a dipole or of an antenna in general. So, if I take the electric field and if I plot the electric field as a function of angle theta and phi, then I get a surface in 3 dimension, and that essentially represents the radiation pattern of the given antenna. Secondly, once we have the electric and magnetic fields from the dipole, then we can find out what is the Poynting vector from this antenna. We can integrate the Poynting vector over the total surface enclosing this antenna, and that will give me the total power radiated by the Hertz dipole. So, in today's lecture essentially we calculate the power radiated by the Hertz dipole, and then we will also see the radiation pattern of the Hertz dipole. So, to start with, the power radiated by the Hertz dipole we first have to calculate the Poynting vector. So, we have electric and magnetic fields. So, the average Poynting vector, as we have seen earlier, the P average, that is there is a vector quantity that is half a real part of E cross H conjugate. Now, since E has two components, theta and r, and H has only one component, phi, essentially we can write this is half real part of E theta H phi conjugate minus E r H phi conjugate. This is going to be in r direction and this is going to be in theta direction. So, the Poynting vector has two components. If I just substitute directly the electric and magnetic fields, the theta and phi, they are in right sequence, theta to phi. So, the Poynting vector will be in r direction, whereas when I go from r to phi, first of all sequence is reverse, that is why there is a minus sign here, and the cross product of r and phi will be in the direction theta. Now, one can show that if I take this electric and magnetic field expressions and I look at these fields which I have here, the ER and H phi, you have here j beta upon r term for H phi, whereas you have beta upon r square term here. Similarly, we have 1 over r square term here, and this term is multiplied by j. So, essentially there is a 90-degree phase difference between ER and H phi. So, this quantity ER H phi, when I calculate, this does not have any real component because there is a phase difference of 90 degrees between these two components. So, real part contribution from this term is 0. So, this essentially is 0, this is purely imaginary. So, the real part essentially would be given by this term. So, that is half real part of E theta H phi conjugate r. We can substitute for E theta and H phi. So, we get the average Poynting vector, which will be equal to half real part of, I can substitute for the electric and magnetic field expressions. So, this is I 0 dl sin theta divided by 4 pi r square 1 upon omega epsilon, and then I have terms because of electric field which is j beta plus beta upon r minus j upon r square, and because of H term which is minus j beta plus 1 upon r. So, you see this term is essentially coming from the electric field which is this term, whereas this term will be coming from here, and we have got a minus sign here because it is H conjugate. So, this becomes minus j beta term. Now, again if I see the terms, the real terms, many of the terms will cancel out. So, only the contribution will come only from these terms, which is j beta and this quantity. So, essentially the real part, if we calculate for this term, that will be equal to half I 0 d L sin theta divided by 4 pi r square beta square upon omega epsilon, and this will be in the direction r. So, it has the unit vector r. So, this also will be in the direction r. So, what that means is that the power Poynting vector which we have, which gives you the power density, that is only coming from these terms which are related to the radiation fields. Other terms which are having a variation as 1 over r or 1 over r square, these terms they do not have a real contribution to the power flow. So, essentially these components of the fields, they correspond to what is called the reactive fields. So, it is that when we are having this quantity purely imaginary and when you have 90-degree phase shift, it is as if we are having some kind of a reactive element there. So, in theta direction the power oscillates, either one half cycle in positive theta direction, the other half cycle in negative theta direction. So, the power keep oscillating, but there is no net power flow in the theta direction, and that makes sense that since there is a completely symmetric problem, there is no preferred direction in which the power can flow. You are having a Hertz dipole which is oscillating. So, half the cycle the current will be flowing upwards, half the cycle the current will be flowing downwards. So, there is no preferred direction in theta in which the power can flow. So, the power essentially is going to flow radially outwards, it is in direction r, and it is solely is going to be because of the radiation fields. So, other fields which are electrostatic field and the induction field, they essentially give you the reactive fields, whereas the radiation field essentially contributes to the power flow because it takes away the power from the Hertz dipole. Once you get this general this thing now, then we can find out what is the total power. This is the Poynting vector, so which is varying as a function of theta. Now, we can take any distance r, take this Hertz dipole enclosed by any closed surface, integrate over the closed surface, and that will give me total power radiated by the Hertz dipole. Now, for simplicity we can take this closed surface as a sphere. So, your integration is simple. So, what we can do now, the total power radiated by the dipole W, let us say, that is equal to the surface integral P average r square sin theta d theta d phi. So, what we have? We have Hertz dipole here, we are considering a sphere around it of radius r. So, the incremental surface area on the surface of the sphere is r square sin theta d theta d phi. So, if I integrate over the total surface area, that means if I integrate over all thetas and phi, then I will get the total power radiated by the Hertz dipole. So, this integral we can write as W equal to, as we know, limits for phi is 0 to 2 pi, the limits for theta is 0 to pi, and I can write down this Poynting vector which I have got there. So, this will be half I 0 d L sin theta upon 4 pi r whole square beta square upon omega epsilon r square, this term sin theta d theta d phi. First thing to note here is that this r square term is going to cancel with this r square term. So, the power radiated should not be a function of r, because we are finding out the r, we are finding out the power which is on any surface of the sphere. So, the total power which is radiated by the dipole should not be a function of what radius we take for the sphere, that should be independent of the size of the sphere. That is what precisely this is telling you, that this r square will cancel. So, total power will be independent of what radius for the sphere you take, that is what should happen. So, if I just substitute now, there is no phi variation in this expression. So, phi integral is very straightforward, it will give me the value 2 pi, and integral is essentially over this theta. So, I have here theta square and this sin theta multiply, that will give me the sin cube theta. So, the power radiated W, that will be equal to half I 0 dl upon 4 pi square beta square upon omega epsilon. Integral over phi will give me 2 pi, integral theta equal to 0 to pi sin cube theta d theta. Now, this integral is very straightforward. I can write down this sin cube theta as sin square theta sin theta, and sin square theta I can write down as 1 minus cos square theta. So, this integral, let us say this is some I1 will be integral theta equal to 0 to pi. We write here sin square theta sin theta d theta, and this we can write as 1 minus cos square theta sin theta d theta, putting cos theta equal to t minus sin theta d theta will be equal to dt. So, this will be the integral 1 minus t square dt, and the limits when theta is equal to 0, this t will be equal to 1 and theta will be equal to pi, this will be equal to minus 1. So, I can substitute into this, and I have a negative sign here for sin theta. So, I can change the limit from minus 1 to 1. So, the integral value will be essentially equal to 4 by 3. So, I can substitute now for the integral value into this expression, and then I get the total power radiated by the Hertz dipole W, that will be equal to, this will give me 16 pi square 2. So, 32 which cancels with this 2. So, I will get a 16. So, that gives me I 0 square d L square upon 16 pi beta cube upon omega epsilon into 4 by 3. Now, if I write down here for beta, that is beta is equal to omega square root mu epsilon, essentially this quantity here omega q upon mu epsilon, that quantity will become, that will be equal to, will become essentially 4 pi square upon lambda square into eta, where eta is the intrinsic impedance of the medium. So, if I rearrange some terms into this, and substitute now for that, I will get the total power radiated by the Hertz dipole, that can be written in terms of the intrinsic impedance substituted here. And if I take the radiation is taking place in the free space, this quantity is 120 pi. So, this one you know for the free space is 120 pi. So, I can substitute here for 120 pi. So, by substituting this into this expression, essentially we get the total power radiated will be 40 pi square I 0 square dl upon lambda whole square. So, for a given current I 0, remember the I 0 is the peak current, because we had taken the variation of the current as I 0 e to the power j omega t. So, this I 0 is the peak current which is flowing in the current element. The total power radiated will be proportional to the square of the current. That is normally the case whenever we talk about the power is proportional to the square of the current. So, that is true in this case also. However, what we note is that the power radiated is related to the square of the length of the dipole dl normalized to the value, that is lambda. That means the absolute length of the dipole is not important. What is important is the relative length of the dipole with respect to the wavelength which you are radiating. So, as the lambda becomes larger and larger, that means the frequency comes down, this dl can be taken physically large enough, so that even then we can satisfy the condition for the Hertz dipole, that is the current is constant along the length, and we can apply this formula to calculate the power radiated by the Hertz dipole. So, the power radiated is proportional to the physical length of the Hertz dipole for a given frequency or for a given lambda. Does that mean that by increasing the value of dl arbitrarily we can increase the power radiated? The answer is no. We can increase the value of dl, but we still have to maintain the nature of Hertz dipole. And what is Hertz dipole? The current along the Hertz dipole is uniform. We have seen right from the beginning of this course that we can assume the current to be uniform when the size of the structure is much smaller compared to the wavelength. So, for uniformity of the current along the Hertz dipole, the length must be much smaller compared to lambda. So, we can say that I can change the value of dl, I can increase it, but still I have to keep this quantity dl much smaller compared to lambda, so that I can call this structure still a Hertz dipole. So, I do not have really a too large a variation in dl, because the dl can be maybe 10% or less than that to satisfy the condition that the current is uniform across the length of the dipole. But within that range, if I increase the length of the dipole, then yes, the power is going to increase for a given current, and that relation will be the square relationship with the length of the dipole. So, this thing now tells me that as long as the structure is much smaller compared to the wavelength, I can treat this structure like a Hertz dipole, and then just using the concept which you have developed, we can calculate the power radiated by the dipole. Now, if I look at this antenna from the circuit point of view, the Hertz dipole, we can excite this antenna by some voltage source which will give me the current in the terminals. So, let us say if I break the Hertz dipole halfway, so I have this is my Hertz dipole now, which is broken into two parts, and this is the input through which the current is flowing. So, if this is connected to a circuit, the current I 0 comes like this, it flows through that, from here it comes back. So, you are having a current which is flowing I 0 in the terminals of the antenna. So, this current is I 0. So, if I see from the input terminal side, since the antenna is radiating and this power is now going away from the structure, if I enclose this antenna in a black box, if I treat it like a black box and just observe the characteristic only on the terminal of this antenna, it will appear we have a current I0 going inside the terminals of the antenna and so much power is radiated by the antenna. That means this box has consumed so much of power. So, if I treat this Hertz dipole like a black box, this black box will appear like a resistance. So, when the current is pumped into that, there is a power loss inside it and that is the characteristic of a resistance. So, this is, I can say equivalently, this is to this box here, which is the black box, and this is equivalent to some resistance which consumes same power as power radiated by the Hertz dipole. So, since this resistance is related to the power radiated by the Hertz dipole, we call this resistance as the radiation resistance of the dipole, and let us denote that by R radiation. So, this quantity R radiation is radiation resistance of the Hertz dipole. So, if I see this dipole from the circuit point of view, then this is equivalent to this radiation resistance. Of course, it will appear like a resistance if we concentrate only on the radiation fields which are contributing to the power flow, but as we know, in the vicinity of this dipole we have also the electrostatic and the induction fields which are reactive fields. So, in fact, between the terminals of this antenna you will not get only radiation resistance, but you will also get the reactance which will be corresponding to those electrostatics and the induction fields. So, in general, the antenna will appear like a complex load. The real part of this load will correspond to the power radiated by the dipole. So, if that is so, then I can ask the power consumed by this one, if I go by simple circuit point of view, will be simply half I0 square into R radiation resistance. So, the W from the circuit point of view should be equal to half I0 square into the radiation resistance. Equating these two now, this is the power which is radiated by the antenna, this is the power which has now gone into the terminals of the antenna. So, these two should be equal. So, this is equal to 40 pi square I0 square dl upon lambda square. So, I0 will cancel out and from here we get the radiation resistance of a Hertz dipole, that is equal to 80 pi square dl upon lambda whole square. And as you have seen, the power radiated is proportional to R radiation for given current. Higher the radiation resistance, more will be the power radiated by the Hertz dipole. So, now we are having a requirement that resistance should be as large as possible. That essentially means dl should be as large as possible, but dl cannot be increased arbitrarily large. So, we have a limited range of dl, that means we have a limited value of the radiation resistance. If I say as a rule of thumb, when the length is about 10% of the wavelength, we can call that is much smaller compared to lambda. If I take dl 0.1 lambda, this ratio will be 0.1, square of that will be 0.01. So, the radiation resistance will be approximately 8 ohms. This pi square will be approximately 10. So, if I take dl approximately 0.1 lambda, then the radiation resistance for this will be approximately 8 ohms. which is a very small resistance. Firstly, if you look at, if I want to excite this structure, I will be using some transmission line for connecting this, and we have seen that coaxial kind of structure we are having characteristic impedances which are of the order of 50 ohms. If I take a parallel wire line for connecting this, then the characteristic impedance will be few hundred ohms. So practically this load appears almost close to like short circuit compared to the characteristic impedances. So you have a great mismatching problem between the transmission line and the antenna when you try to excite this antenna. Secondly, because of the low radiation resistance, the power radiated by this antenna is very small. So radiation resistance is a good concept when we try to estimate the power radiated by a given antenna, and then by devising the mechanism by which the radiation resistance can be increased, we can radiate more power for a given excitation current in the antenna. Having done this calculation now for the power radiated by the antenna, now we can go to the directional characteristics of the antenna, and as I mentioned, this is captured by what is called the radiation pattern of the antenna. So here we are not interested in the absolute electric and magnetic fields. What we are interested is how this electric and magnetic field is varying as a function of angle from the dipole. So if I consider now only the radiation field, that is what we are interested in, then what is the variation of E theta and H phi as a function of angle theta and phi. So if I plot a spherical plot in which the radius vector is the amplitude of the electric field, and if I plot now the electric field as a function of theta phi, I will get a 3-dimensional surface, and I call that as the radiation pattern of the antenna. So all these constants which you are having here, I0, dl, beta square, all these things, these quantities are now taken as constant, because we are interested only in the relative variation of the electric field as a function of theta, and same is true for phi for radiation field, because ratio of E and H is equal to intrinsic impedance, that is constant. That means the radiation pattern which we get for electric and magnetic fields is exactly identical. So since we are now interested only in the relative fields, these factors do not matter. So essentially we have a variation for the electric field which is E theta that varies now as some constant, which includes all those factors like current and length of the dipole, the wavelength and so on, and a variation which is sine of theta. So note the variation of this field is in theta plane is sine theta. So now if I consider this is the location where the Hertz dipole is located, and now the amplitude is not the distance is telling me this amplitude of the electric field. So if I plot the electric field as a function of theta for only the radiation fields, then I will get this plot what we call as the radiation pattern. So let us see, if I put theta equal to 0, which is this direction, so this direction is theta equal to 0, this direction is theta equal to pi by 2, this direction is theta is equal to pi, and the range of theta is from 0 to pi, and then you have a phi variation which goes from 0 to 2 pi, which is in this direction. So the electric field does not have a variation in phi, that means we have a symmetry in the phi plane. So when theta equal to 0, the field is 0. When you go to theta equal to 45 degrees, you will have k upon root 2, and since we are interested only in the relative distribution, we can as well take k as 1. So we have some distance which is 1 over root 2 at 45 degrees. When I take theta equal to pi by 2, this will be equal to 1. Again when I go to 135 degrees, it will be 1 over root 2, and when theta becomes equal to pi, again the field will go to 0. So, the field variation will be something like that. If I vary the value of theta, fix some value of phi and plot this, that is the variation essentially I am going to get as a function of theta. And now, since it is circularly symmetric, I take this pattern and revolve it around this axis, which is the axis of the Hertz dipole. So, around this line, which is z axis, if I take this pattern and revolve it, I will get a 3-dimensional figure, and that is what we call as the radiation pattern of the antenna. So, if I visualize this in 3 dimension, then the structure essentially would look something like that. So, here the antenna, its size and all that are not given, not shown. What is shown is the antenna is taken as a point, and the field which is coming from that point are having a variation sin theta. So, I plot the amplitude of the electric field as a function of theta and phi. I will create a surface which will look like that. This is something like apple. So, the radiation pattern of the Hertz dipole is like an apple. Remember also, the radiation pattern is a 3-dimensional figure. So, essentially we are drawing the variation of electric field as a function of theta and phi. So, therefore, we will get this 3-dimensional surface, and that is what we call as the radiation pattern. However, while drawing or discussing, it is rather difficult to draw 3-dimensional figures, and since this is a simple figure, so if you take sections of these figures, we can still get the information about this 3-dimensional figure. So, what we do is we take 2 sections of this figure by 2 principal planes. One is the plane which is in the phi plane, and other one is the plane which is the theta plane. So, theta plane is the one which the plane which passes through the axis, and that angle, if I take some point here, the plane which contains that point and the axis, that plane essentially will be theta plane. So, in this case, this plane of the paper is nothing but theta plane. So, if I take this apple and cut it vertically, I will get a pattern which will look like that. So, this is the variation of the electric field in the theta plane. That is the reason I call this radiation pattern as the E plane radiation pattern, because the electric field is going to lie in this theta plane. The electric field has only one component, which is theta component. So, this is the plane which is plane of the paper in which the electric field vector is lying. So, electric field vector, as we saw, essentially is in the direction theta. So, electric field vector lies in this vertical plane. So, we call this radiation pattern as E plane radiation pattern. The other principal plane by which we can cut this 3-dimensional figure is plane perpendicular to theta, which is the horizontal plane, and that plane, if I cut this figure at this location where theta is equal to pi by 2, I will get a figure which will be a circle. And since the magnetic field is having a component which is only phi component, this plane essentially contains the magnetic field vector. So, we call this plane, horizontal plane, as the H plane, and the variation of electric field we will get in this plane, which is H plane, we call as the H plane radiation pattern. So, we got now the sections of this general 3-dimensional surface by 2 principal planes. One is the E plane and the H plane. So, this 3-dimensional figure now can be described by two planar figures, which are sections of this 3-dimensional surface in two planes, and these patterns we will call as the E and H plane radiation patterns. So, we get here two patterns, radiation patterns. So, we have a pattern what is called E plane pattern, and we have H plane pattern. The E plane pattern is like figure of 8, whereas the H plane pattern is a circle. So, generally when we discuss about the antennas, since this figure is very simple, most of the time the radiation patterns are given in H plane, which is complicated for the Hertz dipole or for linear dipole, and because of the circular symmetry the H plane radiation pattern is always a circle. So, in the books essentially we see the patterns which will be this, and it is implicitly assumed that H plane radiation pattern we know, and that is a circular pattern. But we should always remember that although normally these two sections for this 3-dimensional figure are given as radiation patterns, the radiation pattern is actually a 3-dimensional surface. That should always be remembered, because many times if we do not remember that, we might come to wrong conclusions, and that we will see little later, that if we do not visualize the radiation pattern properly in the 3-dimensional figure, then it is possible that you might conclude something wrongly. So, we should always develop a habit of visualizing the radiation patterns in 3 dimensions. You should always remember radiation pattern is a function of theta and phi, though we might have simpler sections of that pattern, and we can call those patterns as E plane or H plane radiation patterns. So, radiation pattern is a very important aspect of an antenna, because it tells me which direction the power is going, and as we saw the power is proportional to mod E square. So, the power is maximally going in this direction, no power goes in this direction. So, if I look for this radiation pattern in 3 dimension now, where is the maximum power going? The maximum power going is in the plane which is perpendicular to the Hertz dipole. The Hertz dipole is oriented this way, that is where the dipole was oriented. Along the dipole there is no power flow, and that is a very important thing, that if I consider an antenna which is like a Hertz dipole, there will not be any power radiated along its axis. The whole power will be radiated perpendicular to that, and in this case the power will be radiated symmetrically in all directions. So, the antenna has a preferred direction for throwing the power. It does not throw the power uniformly in all directions. Now, the Hertz dipole is the simplest possible antenna we have thought of, because whenever we have a current there is a direction there. So, what we said, even if we take the simplest possible case of a current which does not have any spatial size, but which has just the orientation, that is what the Hertz dipole did, it had a preferred direction for throwing away the power. That means I can never have a system which will throw away power uniformly in all directions, because even the simplest current element has put the power preferably in certain directions. So, this nature that now the power is not going uniformly in all directions is the directional nature of an antenna, and that is very important. So, it is very difficult or impossible rather to realize in practice an antenna which is what is called an isotropic antenna, which will throw away the power equally in all directions. Now, depending upon the applications, we may require the directional dependence very strongly. There may be situations where we may not require the directional dependence at all. Let me give you the example. Let us say I want to establish communication between 2 points, as we do for example in microwave towers which we see around us. So, I have a microwave tower here, I have a microwave tower here, and the interest is essentially to send the power from this location to this location with as minimal loss as possible. In this case, I would prefer to have an antenna which will be highly directional. That means this antenna should put power only in this direction and should not give the power in any other direction. So, my radiation pattern should be such that it is maximum in this direction and very rapidly dies down as I move away from this direction. So, I will require a highly directional antenna in this case. However, imagine a situation that I have a radio station. This is the microwave tower. The other situation might be I have a radio station and there is a city around it, and we want to have a broadcasting from this radio station. Obviously, now we are not interested in sending the signal from the radio station to a particular house. We want to distribute now the power as uniformly across the city as possible. So, we have now a region which is around this where the radiation should go as uniformly as possible. So, in this case I require an antenna which is as isotropic as possible. So, we can require an antenna which is isotropic. That means it should not have directional dependence. As we argued, it is not possible to get an isotropic antenna in practice. So, you might get an isotropic nature maybe in a plane, and that is what your Hertz dipole does. So, this radiation pattern is not uniform in all directions, but if I go in a direction in the H plane, my radiation pattern is a circle. That means if I ask what is the nature of the radiation pattern in this plane which is H plane, that is isotropic pattern. It is not isotropic as a function of theta, but it is isotropic as a function of phi. So, I may use this structure and I may get a radiation pattern which is uniform in this direction for making use for the broadcasting applications. So, in this case I may have an application which is broadcasting. So, depending upon the situation, I may require an antenna which is very directional. That means it has strongly preferred direction for putting the power, or I may require an antenna which does not have any preferred direction, so that the power goes uniformly in its surrounding. So, in broadcasting application I will get an antenna which is isotropic, which is non-directional, whereas for microwave tower kind of application I will get an antenna which is highly directional antenna. Having understood this, then now depending application we might require to design the antennas which will have certain special radiation characteristic like radiation patterns. Also, in a physical system for a given current we would like to radiate more power. So, ideally the Hertz dipole, though it is very nice to develop the concept of radiation, the Hertz dipole as such will not be a very useful device. What may be more useful is you take a length of the wire which is essentially extension of the Hertz dipole, but now if I increase the length which becomes comparable to the wavelength, I cannot assume the current to be uniform across the dipole, but I can still visualize this linear wire as collection of small Hertz dipoles, and now there is a possibility that this structure which is more physically realizable structure will give more radiation. Of course, in this process your radiation pattern also will get modified. So, in the next time when we meet, essentially we talk about a more practical antenna which is very commonly used, is what is called a linear dipole antenna. So, linear dipole antenna is simply a linear structure like a wire which is excited with some voltage, the current flows on this wire, and then visualizing this wire as collection of the Hertz dipoles, we calculate the electric and magnetic fields, and then we calculate the power and radiation patterns and other aspects of the linear dipole. So, in the next lecture we will investigate the characteristics of more physically realizable antenna, what is called the dipole antenna.